Well, if you observed the patterns that we've had so far when we've been doing integration by parts, we know that we tend to repeat certain things over and over again. And I would say let's consider something like this. If we had x to the fourth times e to the 2x, that means if we're going to take the integration by parts right here method, we're actually going to have a whole bunch of terms based on the fact that in our initial choice, we might do something like setting u equal to x to the fourth so that we can break that down and get a du of 4x cubed dx. And we would take dv to be something like e to the 2x simply because that is an expression that's very easy for us to integrate and get something like 1 half e to the 2x dx, e to the 2x. And every single time we evaluate an integral of e to the 2x, this would happen. Well, look at what's going to happen right here. We're going to get 4x cubed in the next expression. We're going to have to keep repeating this process of writing u and v and dv and du over and over and over again. This is where creating a table can be a really useful thing. So I'm going to set up a short table and show you how we could use that to help us work this through. So in this table, I'm going to have three columns, and the first column is going to have to deal with the sign of integration, right? Because every single time that we use, and when I say sign, S-I-G-N, I'm talking about when we do this trick right here, right? If we have u times v minus v du, integral of v du, right? We have this subtraction sign. But if we had to repeat this a second time, let's say that we could develop a rule for repeated integration by parts, what would happen? Well, the first time we did an iteration of our rule, we'd have u1v1, right, from our first iteration, minus v1 du. But of course, this v1 du, if we take a second stab at this, is going to become the new u, and this is going to become the new dv, and we're going to have to repeat this process over again. And so if we do a second iteration of the rule, what's going to happen is that we're going to get a negative sign that's going to distribute, and we're now going to get a positive sign involved in our expression. u1 times v1 minus u2 times v2 plus our integral of u3 dv3, and if we keep going this way, we're going to have alternating signs going back and forth, u1 v1 minus u2 v2 plus u3 v3 minus u4 v4 plus and so on, right? So what's going to happen right here is that we're going to start out, and we're going to assume we have a positive sign in our first iteration, right before, when I say 0th iteration, maybe we could think of this, before we take our integral, and then in our next one, we're going, that's for u1 and v1, then we're going to have a minus u2 and v2. Then we're going to have a plus u3 and v3 and a minus u4 and v4 and so on down the line for as many iterations as we need, right? We're just going to alternate positive and negative this way. Now the next step, of course, is that we're going to look for u. We had our u that we chose right here and our dv that we chose right here. So in this column, I'm going to put u and all the following du's that would occur. So let's start with x to the fourth, right? That's our initial expression, and then we're going to end up with its derivative, which is going to be 4x cubed, right? dx, pardon me, 4x cubed dx. And what's going to happen right here is that this is going to continue. This process would continue, and in our next iteration, we might see something like 12x squared, and then its derivative, 24x to the third, sorry, x to the first. Don't go too overboard with that differentiation thing. There we go. Okay, then 24, right? And then finally 0, right? Once we reach 0, we would have to stop, right? Because we're not going to have any more u's and du's. Then we're going to have our dv, right, that we start out with, and in this case that's e to the 2x, and we're going to have to figure what's going to happen with the subsequent integrals, antiderivatives of dv that we end up with in each successive step. Right? So what's going to happen? Well, e to the 2x has its antiderivative of 1 half e to the 2x, as we just showed before. In the next step, it would be 1/4, right? 1/2 of e to the 2x. And then the next step, we'd have 1/8 of e to the 2x. And continuing down, what we have? 1/16. Right? Just going by powers of 2 here, right? E to the 2x, and we'd have another step like 1 to 32nds. We could just keep on going this route over and over again. Well, what's actually going to happen right here? Well, essentially, in each successive step, we're going to start off with x to the 4th and e to the 2x, right? But then we're going to have to rewrite. So the way this is going to work is we're going to follow along this pattern. We take our first sign, positive, that's our u, and this is our dv. Right? Okay, so how is that going to look? Well, this ends up being v in our first step. So we're going to end up with a term that looks like the product x to the 4th times 1/4, times 1/2 of e to the 2x, right? And if we were to carry this out, right, we would have been saying minus integral of, what do we say? We'd say 4x cubed times 1/2 e to the 2x dx, and then we'd have to figure out what we'd get from there. Well, we don't need to do this because we've actually already done it off to the side right here. When we take the subtraction of 4x cubed times our next term 1/4, and we're going to get a term like negative 4x cubed times 1/4 e to the 2x. And we're going to go down simplifying each of these at every step of the way. So in our next term, we're going to multiply a positive, oh, get my pen working here, we're going to multiply a positive times 12x squared times 1/8 e to the 2x. And then in our next step, again following the pattern, we're going to have a subtraction of 24x and a 1/16 e to the 2x. And then we're going to end up with another multiplication just following our pattern right here of positive 24 and 1/32. And we know we'll have reached the end when we reach 0 right here, because if we take a negative times 0, well, we're just going to end up subtracting 0 at the end of this whole thing. So our next job would be to simplify and add all of these terms together, so that all of these terms are going to be added together, and this is going to give us our integral. And so what we could do then is to write that the integral of x to the 4th times e to the 2x dx is going to equal the sum that we would get from this big long string of terms, which is this big long string of terms, 1/2 x to the 4th 2 to the x, e to the 2x minus x cubed e to the 2x plus 3/2 x squared e to the 2x minus 3/2 x e to the 2x plus 3/4 e to the 2x. I always think that's a little bit messy, and so sometimes I do like to adjust this a little bit. And so we could actually rewrite this just a little bit once to simplify it. I would factor out 1/4 of e to the 2x and get this long string of terms simplified as 1/4 e to the 2x times 2x to the fourth minus 4x cubed, right? It's 1/4 times 4. That's how we get the 1x cubed. 1/4 of 6x is 3/2, right? 1/4 of 6 is 3/2. So 1 plus 6x squared minus 6x plus 3. That's a little bit easier to handle as far as an expression that we could use later is concerned. But in any case, there we go. That is our answer. So we're done with this one.